Question 2. Halogenoalkanes are useful compounds in synthesis. So I've got a synthesis pathway here, reaction pathway, starting with this chemical. CH2O, CH, CH3, CH2Br. So I've got 1, 2, 3 carbons in a line. So I've got propane. I've got an ol, so I've got propan, and the ol is at number 1. Propan 1 ol with a Br, a bromo at 1, 2, 3. 3 bromo propan 1 ol, and I've got a methyl group on there. The methyl group can actually only go on number 2, so it's 3 bromo, 2 methyl, or just methyl propan 1 ol. Explain why a halogenoalkane is attacked by a nucleophile in this reaction. Reaction 1, nucleophilic substitution. So what you've got is sodium hydroxide in cold water, and the OH minus, the lone pair of electrons on the O of the OH minus, is attacking the C of the Br. It's because the Br is more electronegative than the carbon, so that's creating a polar bond here with the delta plus on the C, and the lone pair of electrons on the O is attacking that C plus and bonding with it. So it's donating its lone pair of electrons into a covalent bond then to the C. That's because that's a nucleophile, a lone pair donor. Br is more electronegative than the carbon. Good. C has a delta plus and Br has a delta minus. The lone pair on the OH minus is donated or attacks the C delta plus. The infrared spectrum of compound Y shows a significant absorption in the range 1680 to 1750. If you look that up, that's a carbon to oxygen double bond. Draw the displayed formula of Y. So if I've got a carbon to oxygen double bond, this OH minus has been turned to a carbon oxygen double bond, so that's made an aldehyde at that end, and if it says it's significant, it's probably got this one converted as well. So both of those OHs, both those alcohols, have been oxidized to aldehydes, probably with something like so it's here, this has been oxidized here in reaction 2, probably by something like acidified potassium dichromate. There we go. So the OHs have been oxidized to aldehyde groups at carbons 1 and 3, and we've still got the methyl group at number 2. Compound Z has the empirical formula. Now remember, an empirical formula doesn't necessarily mean that's its molecular formula. It could be double or triple that. So if it's C3H4NO, well, there's 5 H's in that already. There's 2 O's, so I think it's double that. C6H8N2O, 2 N's and 6 H's. So if I've got 4 C's and it's going up to 6 C's, then I've got CN's attacking. So I've got CN minuses, potassium cyanide is attacking these aldehyde groups. If a CN minus attacks these aldehyde groups, the CN minus joins on. It joins on, the CN minus has got a lone pair and it attacks the delta plus on the C. The lone pair of electrons goes on to the O, makes an O minus, and then the lone pair of electrons on the O then bonds with an H plus, and that's why you need potassium cyanide and dilute acid, because the H plus bonds with the OH minus once the CN has bonded on, and you get 1 on each end. There we are, there's the 2 CNs. I've got the 2 OHs formed from the CO double bond, and I've got the rest of the molecule intact.